Welcome back, my beautiful little marsupials. Today, we're going to talk about our last topic in the unit of energy, and we're going to discuss power. It's that thing that no one man should have all of, or something. I don't know. I don't know how the song goes. Do you know what I'm saying? It's what song is it? It's just called Power. I don't know. It's by Kanye West. It's pretty good. You should go listen to it. But anyway, we're gonna talk about power today. It's pretty tight. Can I write? I bet not. You guys, someday I'll figure this out. All right. So we're gonna talk about power. It is the rate of change of energy. So let's go look at some definitions and stuff. Examine some formulas, make some distinctions, and then we'll do some problems together. So, vocabulary. I don't know why this is funny to me. Just a vocabulary slide with one word seems kind of, you know what I mean? It's like, I don't know. Maybe I'm just telling myself funny jokes again. But power is the rate at which energy is added to or taken out of the system. Power is a scalar, just like energy and work. It can be positive or negative to indicate gaining energy or decreasing energy. But typically you don't look at it that way, right? It's usually just given to you as a number. And it is measured in watts. Let me see if I can recreate this. 1 year, a student drew a picture kind of like this. This is already not looking the way I want it to. Maybe a little more bulbous. It looks something like this. And then there was some like... and then some stuff here too, right? And then this said, you're a unit of power, Harry. And then there was this kid, like this, like this. And it's like, I think he had some hair, maybe. And he's like, I'm a what? What a hilarious joke. Oh my gosh, I died. I thought it was so funny. They handed me this, right? And it's like on one of those little like 3x5 note cards with the lines on it. They're like, you're a unit. I think it's still hanging in my classroom. I might show it to you if you remind me, but I died. I thought this was the funniest joke. So the units of power are watts. A watt, just so we know what watts are made of, a watt is a joule per second. So every second you're gaining 1 joule of energy. That's what a watt is. It's how quickly you're accumulating or losing energy. So let's go and actually I want to talk about one distinction, right? Because sometimes not sometimes, work is the change in energy, not to be confused with power, which is the rate of change of energy. You see the difference? One is like an what's the word for it? A magnitude of change. It's just how much change has occurred. The other one is how much change has occurred and how fast did it happen. Do you see the difference here? So they are very closely related. In fact, work and power are, or work is in the formula for power, but there's a small distinction here that I just want to make sure is clear. So, all right, let's look at some formulas. I have a second joke for you for this one. But I'll tell it to you after the formulas. So the most I think general and maybe useful equation for power is work over time, or change in energy over change in time, change in energy over time, however you want it. It's how much energy you gained or lost and how long it took to happen, or the amount of work done and how long it took to do that work. So I think this is probably the more useful one for us in a high school setting where we don't use calculus. Um, in other contexts, you can separate these variables. You can break down energy and you can break down work. Work is also force times displacement over time. We can kind of break up this fraction, right? We can move the f outside of the fraction like this, and then just put it in change in x over t. Change in x over t is velocity. So another formula for power is the force being applied and how fast the thing is going when you apply that force. The reason I think that this is not super useful or super intuitive for us is we don't often look at cases where something has a force being applied to it and it's moving at a constant velocity, v equals a number, right? Usually when we're applying forces to things, they're unbalanced forces and they are the object is accelerating. If you're accelerating, this formula doesn't really make sense because this is a change in displacement over time. This is an average velocity. So it gets a little weird. It's clunky to use. And it's clunky to measure these forces. One case where this would be really useful would be if you have like a car or a plane that's cruising at a constant velocity. If they're going fast enough, there's a significant amount of something like air resistance holding them back. And the air resistance is what's keeping them from accelerating more. So it makes sense to kind of multiply the force times their constant velocity at that point. But this force is notoriously difficult to measure. So for our class, we're probably not really going to mess with this too much. This topic, power in general, is not really a very large percentage of our tests at the end of the year, the AP test that we're aiming for. So we're not going to worry about it too much. If it comes up on the AP test, write me a letter and tell me that I failed you or something. I don't know. Sorry if it happens, but we're doing the best we can here. So, all right. So let's talk about power in the ways that you will see it most often out in real life if you ever get to leave high school. So one of the most common places you'll see power is people will talk about cars and boats and planes and machines, and they'll say it has this much horsepower. So let's talk about what is 1 horsepower. How much is that? Because I don't think that's necessarily intuitive, right? How much is a horsepower? Can I make a horsepower? Can you make a horsepower? I don't know. Let's see. So when they were creating the horsepower way back, I think horsepower comes from right about the time when steam engines and such were made. And they made a steam engine and then they compared it to like how quickly it could do something compared to how quickly a horse could do the same thing. So the thing they made the steam engine and the horse do was lift some weight up into the air, right? So they attached a horse to a 75 kilogram mass and they made them lift the mass 1 meter into the air. So from the ground up, this is going to be 1 meter. And the horse took about 1 second to do that. So let's calculate the power produced by the horse lifting this mass. And And then we'll see how many watts that is. And then we'll say this many watts is 1 horsepower. And we'll talk about, just some general numbers and stuff. So, how are we going to calculate this? Our formula for power that we're going to use here is going to be change in energy over change in time. So the energy that this box is going to gain by being lifted 1 meter into the air is gravitational potential energy. So when it's up here, our energy final is gravitational potential energy. At the bottom, we'll say here is H equals 0. It has no gravitational potential energy, and we're going to ignore how fast it's moving when it's going up. It starts at rest, the horse lifts it a second, and then stops, right? There's like a dude here with like his little straw thing. He's got like his straw hat on. You know the sort, right? And he's got overalls, and he's leading the horse by like some reins. Or maybe the horse eats carrots. I don't know. Whatever. You get the idea. So we start with no energy because we're on the ground and we're not moving. Then we lift it 1 meter, and then we have gravitational potential energy. So our change in energy is just the total amount of energy we have at the end, which is mgh. The mass of the block is 75. The g that we use is 10, and the height is 1 meter. So our change in energy is 750 joules, and it took 1 second to do that. So a horsepower is about 175 or 170. No, holy cow, you guys, reading is hard. 750 joules per second, or 750 watts. If you Google it, 1 horsepower is equal to 735.75 watts. The place we get this number from is when you calculate this number, they're using for G 9.81, which is a little more accurate. We could use that, but we round to 10 because high school and, So this is the conversion rate. Let's talk about how hard this would be to do. So 1 meter is about a yard. It's about 3 feet. It's a little over 3 feet. I think it's 39 inches. 75 kilograms is actually quite a bit. 75 kilograms is like 160 pounds. So this is like lifting a medium to big sized high school boy, probably, if we're doing averages, statistically speaking, 1 meter into the air and taking 1 second to do that. So you go 1 Mississippi. If you think you could lift your classmate 1 meter into the air, just 6 feet, that's like chest height, you could probably make a horsepower. Realistically, humans can make 1 horsepower. The issue is they can't sustain 1 horsepower for very long. This is actually really, it's hard to sustain for very long. Because, let me tell you an allegory. When I was going to college, I'm not going to tell you which college I went to because they don't pay me enough to shill for them. I was walking around near the student union, which is where you get food and snacks and stuff at lunchtime. And sometimes they would have a bicycle hooked up to a machine, right? This thing would be on some rollers, so you wouldn't go anywhere. And this thing would be hooked up to like a blender. Okay. And they'd say, do you want to try and power this blender with just your legs using a bicycle? And they'd throw some fruit in there, and then you'd hop on the bike and you'd spin your bike as fast as you could for as long as you could, and you'd blend up the fruit And then they'd say, here's your smoothie. And they'd like give you a little cup of smoothie. And then you'd be like, I made this smoothie with my own legs. And I don't remember how strong the blender was. I think it's like a 300-watt blender or something. Most microwaves are like 1500. They're like 2 horsepower microwaves. But this is like a little shrimpy blender. It's like 300-watt blender. People would go, yeah, I could do that. This will be easy. And they'd hop on this bike and then they'd spin and spin and spin. And the blender would like chirk, 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 chirk. And it would just barely blend the fruit. And they get just like fruit chunks. It was so funny. But this is really hard to do. Professional cyclists, like people who ride in the Tour de France and like the Giro d'Italia and all the like really big bicycle races, professional bicycle racers can maintain about 330 watts for 1 hour or so. This is kind of like, if you can do that, you're almost cut out to be a professional cyclist, or at least you got the legs for it. Regular humans like you and me, I have a bicycle trainer at home, and it like hooks onto my back wheel, and I can ride indoors, and it tells me how much power I make. If I do 140 watts, I can hold that for about an hour, but once I get off, I'm drenched in sweat, I'm dying, and my legs hurt, and I do this like semi-frequently, not to toot my own bicycle horn, but this is like a more regular human kind of power to make. Okay, cool. Interesting. Maybe not interesting, but fun, you know. And if you don't think it's fun or interesting, then you're wrong or something. I don't know. Sorry. I didn't mean to get upset. Next slide. All right. This is a lab activity we used to do in the before times. So let's talk about it. I think it's still fun to talk about. So we have a 70-kilogram student running up bleachers for practice. They could be on soccer team or badminton team or volleyball team or whatever. The bleachers are 4.5 meters high from the bottom. The student takes 3 seconds to run from the bottom of the bleachers to the top, starting at rest and immediately coming to stop. How much power did they produce doing this? So this student is going to just run to the top, and then I think at the top of the bleachers at school, there's like a fence here so that you don't fall off. So they run to the top and run into the fence and stop. So what we're going to do here is the same thing. Power equals change in energy over change in time. So our energy, again, we are going to gain gravitational potential because we are lifting up our body into the air. The height of the bleachers from the bottom to the top is 4.5 meters. The mass of the student is 70 kilograms, and it takes 3 seconds. So our work or our energy, our change in energy, goes from 0, because we're at the bottom, starting from rest, and it goes up to the mass of the student times g times h, divided by the amount of time it takes. So plugging in our numbers, this is going to be 70 times 10 times 4.5 divided by 3. So this is 700 times 4 would be 2,800 plus another 350 would be 3,150 joules of energy divided by 3. So we produce 1,050 watts of power. So again, this is more than a horsepower. Humans can pretty easily produce more than a horsepower. But are you going to be able to sprint at this speed up bleachers for more than 3 seconds? If you had a mountain as steep as bleachers, could you run up the entire mountain as fast as you ran up these 4.5 meters of bleachers? No, you'd probably run this fast for maybe like 3 or 4 stacks of bleachers, and then you'd get real tired real quick and then run out of gas. So there we go. Pretty fun. All right. Let's do one that's not about gravity. So a car owner is bragging about how much horsepower their car has. And this is a very typical thing if you know anything about cars and people who like cars. Their favorite thing to do is talk about horsepower and torque and all these other physics numbers that they don't really understand very well. They claim their car has 300 horsepower, which I've been led to believe is a pretty modest amount of horsepower for quote unquote fast cars. But you know. And they say that their car can do 0 to 60 miles an hour in about 60 seconds. The mass of their car is 1,370 kilograms. And I've already done the unit conversions for you, so you don't have to trip out too much. And 60 miles an hour is about 27 meters per second. 735.75 watts is 1 horsepower. So what we're going to do is we're going to calculate the power of this car as it goes from a standstill to 60 miles an hour. And then we're going to see, is that 300 horsepower? So what kind of energy do we have at the beginning? Energy initial is going to be 0 because they're not moving, they're not raised up, and there's not a big spring anywhere. So we don't have gravitational, we don't have elastic, we don't have kinetic. Then the person in the car floors it, and then their car peels out a little bit, makes a little skirt, and then they accelerate and gain kinetic energy. So E final will be kinetic energy. So kinetic energy is 1/2 the mass of the object times its velocity squared. So we're going to plug that in. Our power is going to be whatever this number gives us, because final minus initial 0, so it's just the final. We went from 0 to this. So we're going to have 1/2 mv squared divided by the time it took us to get there, which is 6 seconds. So this is 0.5 times 1,370 times 27 squared over 6. So let me go ahead and type that into my calculator. So 0.5 times 1,370 times 27 squared divided by 6. And we get power equals 83,227.5 watts. All right, this is in watts, and we need to now convert this into horsepower so that we can tell if this person's just pulling our leg or maybe they got swindled by the dealer or something. So unit conversion, we have 83,227.5, whoops, missed my 7.5 watts. We need to multiply that by a ratio. We want the watts to cancel, so we're going to put the watts on the bottom. 735.75 watts is 1 horsepower. So we're just taking this number and dividing by this, and then that'll tell us horsepower. So divide by 735.75, and we get 113.12 horsepower. This is much less than 300 horsepower. So their car is not as horsepowery as they'd like to believe it is. And I admittedly am not a huge car buff, but this seems like fast to me. I don't know a lot about cars. Some disclaimers. If you are into cars, there are different ways you can measure horsepower of a car. There's what is called rear wheel horsepower, where you put this thing on what's called a dynamometer, I think is the word for it. It's basically like a big drum, and then you give it the beans, and then it spins this thing, and this thing is attached to like a machine over here, right? And it's got like a little screen, a little lever and whatnot, and then it spits out 113 horsepower, right? So there's rear wheel horsepower. There are other ways or other types of dynos. Some of them take motors and they hook it up directly to what's called a flywheel, I think. No. It's your crankshaft or something like that. I'm not 100% sure. I'm not a mechanic. I'm a math teacher. They hook it up to the motor directly. So there's not all this like connecting stuff in the middle with friction. They hook this thing up to the same machine. And then this number is generally like a little bit higher than this number just because you don't have all of your like drivetrain and flywheel and like gearboxes and transmission and stuff in the way. So you get a little bit higher numbers, which are, I don't know. It's not like measuring it here makes your car faster after you've measured a higher number. It's not like you type in the number to your car so your car knows how fast it's allowed to speed up. If you put this back in this, you'll get a smaller number like that. But anyway, so this is one way you could measure horsepower, is you could time it and you could calculate it this way and you get an estimate. But I don't know how good this estimate matches up with these measurements. So yeah, anyway, it's fun. It's good practice. All right. Last question we want to talk about. This question I made up myself, and I'm quite proud of this because it's eerily similar to what I think would be like an AP question. Since we just did some AP question practice the other day, this reminds me a lot of an AP question, right? It's nice and vague. It's got no real numbers in it, and it's like, here's how it's set up, what it do, right? So there are two spheres. Oh, dang. I already messed up my own question. Pretend these are round. Being dropped. One sphere has a mass of m, some mass, and is dropped from a height h. That's this one right here. So this height is h, this mass is m. The other sphere has a mass of 0.5 m. It's half as big and is dropped from a height of 2h. So this sphere weighs half as much, or rather has half as much mass, but is 2 times higher. What we want to compare is how much power is produced by gravity as the spheres fall. Interesting question. So when we say compare, here's your options. Option A, same. Option B, the big one, mass, let's see, gravity produces more on mass m. C is gravity is more on 1/2 m. So this power is bigger, or this power is bigger. Or D, of course, not enough information. We can't tell. So let's try and answer this. So the first thing we should do is we should think to ourselves, okay, we're talking about power. The equation for power is work over time or change in energy over time. Okay, so we need to investigate some energy. Let's look at the types of energy that we're going to be looking at for this problem. Both of these spheres are dropped, meaning they're released from rest, so V naught equals 0. So no kinetic energy at the beginning. No springs anywhere. We're not dropping them onto rubber bands or trampolines. So no elastic energy. They are raised up to a height and released and let to fall. So what we're looking at here is gravitational potential energy. Okay. So we'll call this UG1 and UG2. For our gravitational potential energy, it is mgh. So let's look at this one. The gravitational potential energy for this one is going to be capital M G times capital H. That's our gravitational potential energy here. For UG2, it's going to be 1/2 m times g times 2h. The 2 and the 1/2 cancel, and we get capital M, G, capital H, which is the same amount of energy for both systems. Because this one's heavier, it's harder to get up there, so we're going to get more energy back out of it. But this one is raised twice as high to compensate for its lack of mass. So the total amount of work done is the same. So the change in energy is the same. The only difference here is going to be the time to fall. Okay. Which one's going to take longer to hit the ground? Well, everything on any planet, as long as you're close to the surface, has a constant acceleration. Acceleration in the y direction equals g. So this one is going to accelerate down at 10 meters per second squared. This one will accelerate down at 10 meters per second squared. If they have the same starting velocity, the same acceleration, but this one has to go farther, it's going to take more time to do that. So because this one has a bigger time, if we divide by a big number, we get a smaller number. So this one will produce less power because it takes longer to create the same amount of energy. So we can say the gravity produced by gravity on the bigger mass will be bigger because it creates the same amount of kinetic energy when it hits the ground, but it will do so faster. Cool. Tight. There we go. I like that one. I'm very proud of this. This seems like a very sneaky problem. I don't know that everyone... I think the temptation here is to say time is equal because the kinetic energy at the end is equal or something. I don't know. They'll be going the same... Oh, they won't even be going the same speed, will they? They won't. Okay. Anyway, very interesting problem. I like that one. So, if you have preguntas, please go to the WebEx and say, Mr. Barton, you did a terrible job with that video. I need you to re-explain this problem, or this concept, or this formula, or this definition, or this joke. That joke wasn't funny. I didn't get it. You have to explain it to me. I'd be happy to. Go ahead and hop in the WebEx and let me know how you feel. Until next time, have a wonderful day. Stay safe. Like and subscribe.